Okay, we're starting. So let's finish up those examples and then move on to the topic of the day. So this is just us differentiating a bunch of stuff. We were on 16. Let's just find the derivative of x over x cubed. 17. Derivative 2x plus 1 to the 8 times x squared plus 1 to the 5th. 15. Okay, 16, how do we do it? Quotient rule, okay. So the derivative of x over e to the x cubed, what does the quotient rule say? Okay, which is? What derivative of e to the x cubed? Yeah?
Is it e to the x cubed times 3x squared?
3x squared e to the x cubed. Right? Because derivative of e to the u is just u prime e to the u. Over.
Ex cubed
Can you simplify? From the top, we could factor out an ex cubed. What would we have left? 1 minus x cubed over e to the x cubed squared. This guy now cancels with that guy, and so we have 1 minus 3x cubed over e to the x cubed. 17. How do you find the derivative of 2x plus 1 to the 8th times x squared plus 1 to the 5th? What do we use here?
Is it the chain rule?
It would involve the chain rule, sure. But how do you go about applying it?
Like you would use a product rule?
You use the product rule, you see two functions multiplying each other. So you know ultimately you're using the product rule, so how would that look here?
8 2x plus 1 is 7 power times 2.
So in order to differentiate the first one, you need to use the chain rule, which says you differentiate the outer function, then multiply the derivative of the inside. And? Leave that one alone. Then? Plus
5x squared plus 1 to the 4th times 2x.
Differentiate the second one and leave the first one. Again, notice that I'm applying the chain rule here. Can you simplify that for me? As in factor. How would you factor? It's going to help us out with 18, so there's a reason why I'm going through the trouble.
2 to the 7.
Huh?
2x plus 1 to the 7.
So 2 is a common term. 2x plus 1 is a common term. X squared plus 1 is a common term. So you factor out all the common terms. So 2 times 2x plus 1, x squared plus 1. What power of 2x plus 1 do we factor out?
4. Wait, no, 7.
7. You factor out the lowest power. What factor?
4.
So that would be 4. Now with open brackets, what do we have left over?
X we
8. That was the first thing that's here. We didn't do anything with the 8. This guy, we took him out. The 2, we took him out. Here there were 5 factors. We took out 4 of them, so there's 1 factor left. Then you move to the next term. Plus, what do we leave? 5? It's there. This guy, we took that out. The 2 we took out, so there's just an x left.
And then 2x plus 1.
And this guy, we took out 7 factors, so there's a 2x plus 1 left over. Yeah.
I don't understand where you got the 2x from.
Chain rule.
Okay.
Derivative of the outside multiplied by derivative of the inside. Derivative of x squared is 2x.
Okay.
So that's the chain rule we apply here. At this point, we can simplify a little bit. So this guy, you realize this would be 8x squared plus 8, plus this would be 5x, 10x squared, plus 5x. So you can combine all of those and you would get 18x squared plus 5x plus 8. So that would be the answer. What about this one? Oh, 18. It's the 2x plus 1 to the 8, and we divide by the x squared plus 1 to the 5th. Quotient rule. So what would that look like here?
X squared plus 1 to the 5.
Well, it's the bottom times derivative of the top, right? Which is kind of going to be this, minus the top times derivative of the bottom. It's going to be exactly this, except the middle sign is going to change. So you take the derivative of this guy times that guy, x squared plus 5 to the 5th, minus, that's where the difference is going to come. Now you take the derivative of the denominator. All over the bottom square. Now this particular example won't look familiar to you, but in principle it's very similar to an example that you saw on test 1. So in problem 1b, I asked you to simplify something. It turns out that thing that I asked you to simplify was something I just did the quotient rule on, and I just put the expression there and asked you to simplify it. So this would be the derivative, but we want to simplify for some reason. Right? Because, for example, there's going to come a point where we're going to want to be able to set the derivative equal to 0, and solving that would involve us factoring and simplifying. So how would we simplify?
Put a 2 and x squared plus 1 to the 4.
It will pretty much be exactly
Yeah.
this, right? You pull out the common factors. The difference is instead of a plus here, you're going to have a minus. So we're saving ourselves some work here. But it's the same idea, the same process we went through here to figure that out. We're going to do that here to figure out the numerator here. So it's going to look pretty much like that. It's going to be 2 times 2x plus 1 to the 7 times x squared plus 1 to the 4th. Then we'd have 8 times x squared plus 1 minus 5x times x times 2x plus 1 all over the bottom square. Now at that point, this can cancel with 4 of those, so that's left over with 6. And on the inside, we'd have 8x squared plus 8. This would be minus 10x squared minus 5x. Nothing else really simplifies, so this becomes 2 times 2x plus 1 to the 7th times 8x squared minus 10x squared is minus 2x squared minus 5x plus 8 all over that. So that mess becomes this guy. So that's just getting us used to derivative rules. We need to know them for the next topic definitely. To be very familiar with these rules. But that's the one. Speaking of rules, how do I define f prime?
In terms of limits,
Mm-hmm.
limit is h approaching 0 of f(x) plus h minus f(x) all of h.
What's the power rule? Power rule.
N x to the n plus
No, that's one side of the power rule. What's the power rule? It starts out with the derivative of what kind of expression? X to the n is equal to? What's the product rule?
Derivative of x of f
Derivative
times g
of f times g
equals f prime of g, f prime times g plus g prime times f.
Quotient rule? Right, the low D high high D low. What about the chain rule? What does the chain rule say? Right, so this is when you have a composite function, you have a function inside of another one. This is going to be super important to the next section. How do you do that? Derive the outside times the derivative of the inside, g prime. Knowing the rules are very important. These rules will always be true. Just because you change the context in which you're applying these rules doesn't make them any less true. We're going to change the context today. But these rules will always apply. In fact, in the first topic that we're going to be covering, it's really an application of the chain rule. Right? So knowing the chain rule itself is going to be very important. We're going to look at 3.5. Let's talk about implicit differentiation. And log differentiation. Two new derivative techniques. Not rules, these are techniques, right? We will be applying rules to do these techniques. So the rules are very important, you need to have them memorized. You need to have them memorized to the point where you kind of see them as templates being able to fit on top of some random problem that you're doing, and you can figure out what you're doing. So here's the idea. We'll do implicit differentiation first, and then, because log differentiation involves implicit differentiation, so we're going to do this guy first. There are two main ways to define a function, really. One, we can say we define that function explicitly. This is kind of how you've always defined functions your whole life, right? This says y is equal to some function of x. This is called the explicit definition of a function because your dependent variable is on one side by itself, it's explicitly out in the open, and it's equal to some formula that involves the independent variable. That's called an explicitly defined function. So examples of that is like y equals x squared, y equals 1 over x, y equals the radical of 2 minus x squared, etc. Right? Like kind of what you think of when you think of a function. But it turns out there's another way to define a function. It's called implicit. So a function can be implicitly defined. And basically what that means is you cannot have the y out in the open, or it's just not given to you that way. This means like you have a function of x's and y's mixed together equals something else. So an example of that would be something like x times y equals 1, or x squared plus y squared equals 4, or 2xy minus 3 times the radical of xy plus y to the 4th equals 7x, or something like that. This is said, the function in this case is said to be implicitly defined. So I'm thinking of my y as some function of x, but it's not out in the open where I can just say y is this thing. This is the rule that with x is. Here your x's and y's are mixed together. They're intermingled. And you may or may not be able to solve for y. In this case, you can solve for y pretty easily, but it's a lot harder in this case, for example. So we say this is implicitly defined. Now it turns out that there are many times when we find out the relationship between two things, the answer is an implicit answer. Meaning you can't really isolate one of these things and talk about it strictly in terms of the other thing. You kind of have to describe the relationship as these two things work together in this way, and you get an equation like that. Right? Which I'll give you a specific example of that from chemistry, for example. Right? But this is kind of what I mean. You can define a function explicitly or implicitly. You can have the y by itself on one side and a bunch of something else that doesn't involve y on the other side, or the x's and y's can be commingled and mixed together. However, just because this is a rule that I get and I get it in this form doesn't mean that I don't want to be able to use calculus. I would still want to be able to use calculus. I would still want to be able to talk about how fast is y changing with respect to x, or how do I find a tangent line, or how do I do whatever thing that calculus helps me to do. Right? I still want to be able to perform calculus in this way, and the question is, how do I do that? The answer is implicit differentiation. So those are the two main ways to find a function. This way we kind of know how to deal with. To deal with this, to find derivatives, you just use the rules that I have you guys repeat just now. Right? Here, that's a little bit more tricky. Well, it's not really tricky. It's going to be an application of the chain rule. So the question is, how do we find y prime, or specifically dy dx, in the implicit case? The answer is implicit differentiation. By the way, this is just an application of the chain rule, and I'm going to give you some examples that kind of bring that to light. So I'm going to give you a bunch of expressions that I want you to find the derivative of. And then I can sort of explain to you how implicit differentiation is going to happen. So derivative of some function f of x. Right, too much space for that guy. Like, yeah, you're laughing because like, what? That's nothing. Okay, what about I make it a little bit more complicated? What if it was f of x, but now I squared it? Oh, now things are getting serious. Okay, what if it were the derivative of x squared times that function, whatever it is, squared? What if I ask you the derivative of x divided by f of x? Find the derivative of these expressions. F of x is some function. I'm not going to tell you what it is, but it is differentiable. It's possible to find the derivative. What about the first one? What's the derivative with? It's just f prime. Okay. I don't know what the function is. That's literally the best I can do. Okay, dy dx, it's f prime. What about this one though? How do you differentiate that?
Would that be like the chain rule itself?
It's the chain rule. Pretty much the chain rule. What does the chain rule say we would do?
It'd be f of x combined with f of x times, wait, f prime of x with f of x as the x times f of x. I have no idea what I'm saying.
The chain rule is right, but how would you apply it here? Yeah?
Wait, can you use power rule? Or no?
What was the chain rule say?
Wait, can you bring the 2 in front and then keep the fx in and then times f prime of x?
Right. Here I have an outer function which is a square. There's an inside function. So how do I differentiate that? Differentiate the outside, which I know how to do by the power rule. That's going to be what it is, times the derivative of the inside. So the derivative of this expression would be that expression. It's kind of like when we had that x cubed plus 1 to the 5th. You just differentiate around the x squared plus 1, then you multiply by the derivative of the inside. I would do the same thing here. So that's the chain rule. That would be the answer. What about this one? Yeah?
You use the product rule.
Use the product rule. Just because there's some function that you don't know what it is, doesn't mean the product rule stops working. The product rule always works. I have one function times some other function. How do you differentiate that? Yeah?
The 2x, no, it's the derivative first, so 2x times f of x squared plus the derivative of your g, so like
So the x squared stays, and then
Yeah.
you're going to
2 times f of x, and then times f of x, no, f prime of x, yeah.
that would be the derivative of that expression. What about the one that I erased? What is the derivative of x divided by f of x? How do we do that? Quotient rule. It's one function divided by another function, so what would the quotient rule say?
X prime. X. Wait, that's just 1, right?
Right, the derivative of the top times the bottom minus
X
the top
times f prime.
derivative of the
F
bottom
X, yeah.
over the bottom squared. And that expression is the derivative, whatever that. What the f of x is, I don't know, but to apply the rules of derivatives, that has to be the answer. That has to be the form of the answer. So here's what I'm going to do. We're going to do these exact things because I just want you to see them as templates. But now instead of calling it f of x, I'll just call it y. So let's redo these examples right below each other. I'm just going to rename things, right? So instead of saying d dx of f of x, what is d dx of y? And instead of saying d dx of f of x squared, what is d dx of y squared? What is the derivative of x squared y squared? What is the derivative of x divided by y? What would these expressions be? Let's start with the first one. Just y prime, right? This is just saying the derivative with respect to x of y. What is that y prime? What about the derivative with respect to x of y squared?
2
Times y prime.
Yeah.
Now the question is, why did I multiply by y prime? Chain rule. You multiply by y prime here for the exact same reason you multiplied f prime there. Right? This y is not just, you don't think of it as a single variable. It's not your independent variable. It's not an x. Which means you have to think of it as some other function that you don't know what it is. But that just means now it's an inside function. So you just differentiate the outside, multiply by the derivative of the inside. So whenever I differentiate a y term, I multiply by y prime. What about this one? Hmm?
2x times y squared plus x squared times 2y times y prime.
That would be the derivative of that expression. Notice what is happening here. When I differentiated the x, I didn't really do anything. When I differentiate the y, I have to multiply by y prime. Y, chain rule, right? It's just an application of the chain. Yeah.
For y prime, would we also write like dy dx?
You could. Those are interchangeable.
Okay.
It's just an alternative notation. Like I mentioned, when I write y prime, because I'm lazy, dy dx takes longer to write. The dy dx notation, you really use that when you want to emphasize who the independent variable is. So as opposed, if I just write y prime and someone doesn't know what my independent variable is, me writing dy dx tells them that the x is the independent variable. This is considered a different derivative from if I said dy dt, for example. Right? So if I want to emphasize who the independent variable is, am I plugging in a length or a time, I would write it in this expression. But if it's understood, we all know that x is the independent variable, writing y prime is okay. So I really only use the other notation if I really want to emphasize, but otherwise I'm too lazy to like write dy dx all the time. When we really get into solving these problems, you'll see why it's going to be annoying having to write them all the time. But the idea is the following. You see an expression like this, product rule and all that still applies. This is still one function times another function. The difference is the y is some inside function that I don't know, so whenever I'm differentiating a y term, I need to apply the chain rule. Differentiating x term is just normal. What about this one?
Times y.
Same thing. It's a division of functions. So it is the top, the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. That would be the expression. So we're applying the same rules. The difference is there's this y that we're carrying around. That's really some function on the inside. And so we have to apply the chain rule every time we're differentiating that term. That's kind of implicit differentiation in a nutshell. Let's actually see it in a problem. Find y prime, which by here I mean dy dx. Here's the first example. xy equals 1. So you're given that relationship between two quantities, find the derivative. Go.
Can you find the derivative of both sides or no?
You can do that, right? If this is equal to that, then the derivative of this must be equal to the derivative of that. Yeah. So what would happen?
Derivative. Product rule?
Product rule.
Yeah.
There's two functions being multiplied here. We can do the product rule. So what is the product rule?
1 times y plus x times y prime.
Right. Y is some function I don't know, so its derivative I just write y prime to represent its derivative. What's the derivative of 1?
0.
0. So what you just did was implicit differentiation. Right? You implicitly found the derivative. We're not done yet though. The goal is to find y prime, right? Which means this is the guy I care about. How do I find him? Yeah?
Like, if you say if you were solving for that variable.
Yeah, just solving algebra is how I'd find him. Whatever algebra techniques I need to do to solve that equation, just do it. In this case, just bring that to the other side. And then divide both sides by x. And so this I would consider my answer. Question. How do I know I could divide by x? What if x is 0? Is that okay? Huh?
Then is your derivative of your function at that point just doesn't exist. It could be like a sharp point.
Sure. Is that something I have to worry about with this particular example? Can x be 0?
Oh no, because it equals the 1.
Right, we know this fact, so we know that our x is not 0. So I can divide with wanton abandon. Like I know it's never going to be a problem. Because if x were 0, there's no way this would give me 1. So this division here is well defined. This derivative will make sense on my function on everywhere the function itself is different. So I don't really have to worry about that. Could we do this using explicit differentiation? Some of you probably thought of that, like why? Was there another option here?
Divide the x.
x is not 0, so I could have just divided by it from the beginning, right? And how would I find y prime now?
Plug in 1 over x for y. I think.
It's already here.
Oh wait, I was looking. Wait.
So I could have solved for y. I'm doing it completely different way.
X to the -1.
Right, this I think of as x to the -1, so how do I find its derivative? Power rule, which gives me,
-1 x minus 2.
right? Or this is minus 1 over x squared, in other words. Okay. This is an example of a problem that I could do it either implicitly or explicitly. Here's an issue I have though. The answers look different. Are they actually the same? Well, we kind of know that this is the answer, but is that answer valid? How would you reconcile these two? Is the answer minus y over x, or is the answer minus 1 over x squared? Can you reconcile these two?
Are they the same thing?
Hmm?
Are they the same thing?
I'm asking you, are they the same thing? How do you know they're the same thing? This is the way we've always done it. We kind of know this is true. We proved the power rule. So we're pretty confident this is the answer, but that doesn't look like that, really.
But like either way, it's still the
Yeah, but justify to me that this is a valid
Can't you
answer.
just plug the fact that you have 1 y equals to 1 over x, can you just plug it in there?
Yeah,
and
I
then-
could do that.
Yeah.
Right. Look, I can replace that y with 1 over x, and then it's over x, and then that simplifies to minus 1 over x squared. Right? So this answer is actually exactly that answer. Right? I just want you to see that this is actually a valid answer, and it agrees with the answer that we know we should get. You won't always be able to do that, by the way. I'm going to give you examples where you can't do that. But it's nice to see that, okay, it kind of works out. Right? This is an example of a problem that you can do implicitly or explicitly. It just depends on your mood at the time. Here's another problem. Right? Neither of these are particularly hard. The answer seems to be in different forms, but they're really the same. What if I ask you to find, it's the same problem here, find y prime. But what if I asked you about, 5x squared plus 2x times y plus x to the 4th y squared equals 4x cubed. Now there might be some people who are talking about, well, why did we need implicit differentiation at all? Like I could have just solved for y and find the derivative the old way. What is the point of this? It looks more complicated, there's a y in my answer, what do you do with that y in the answer? Okay, what about that guy? Could you solve for y there and do it the old way?
I guess you could for the sake of that.
You could solve for y. Do you see how? How do you solve for y in that? Does it help if I do this? I'm going to replace all the expressions of x's with letters, like. Can you see it? What kind of expression is this? It's a quadratic, which means I do know how to solve for that. I could use the quadratic formula, for example. The quadratic formula always works. So I could solve for y here. This would mean that, well, x to the 4th y squared plus 5x squared plus 2x times y minus 4x cubed equals 0. And then I can apply the quadratic formula where this is my a, that's my b, that's my c. So this is minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So this is an example where I could solve for y if I wanted to, but would I want to? If the goal is to find y prime, is that something you want to have to find the derivative of? Sure, you could do it. Would you want to do it though? That's another question entirely. So yeah, okay, find y prime. Okay, it's probably a quadratic. Okay, boom, 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 quotient rule. Have fun. You can spend the entire exam time figuring out the quote, doing that with the quotient rule. There's a better way. Let's use what we've learned about implicit differentiation and find y prime. How do we go about it?
You just take the
Take derivative of both sides like we did last time, just differentiate each term separately. What about this term? How would I differentiate this term? One term at a time. Product rule. I have one function times another function. Product rule still is the thing. Still works. So I would differentiate one, leave the second. Plus, I would leave the first. Differentiate the second. Derivative of y is y prime, whatever that means. Plus, how did I differentiate this? Product rule again. Again, it's one function times another function. Product rule applies. Differentiate the first function, leave the second, plus leave the first function, differentiate the second. What's the derivative of y squared?
2y, y prime.
Y prime, because the chain rule applied. Every time I differentiate the y term, I will multiply by a y prime. So that's the derivative of this guy. What's the derivative of 4x cubed?
12x squared.
So now I have that expression. My goal is to find y prime. How do I do it?
Combine.
Yeah, algebra. Algebra is how I would do it. Here's my y prime. I have two of them hanging out over here. So I want to solve the equation for y prime. So what would I do? Well, take everyone that doesn't have a y prime in it and move it to the other side. That's how you solve an equation. So I have the 12x squared here. I would just subtract this guy. I would also subtract this guy. And that's it. Everyone else has a y prime in it, right? How do I deal with this, the left side? What would you do? Now we have this two left over. How do I get to the y prime?
Can we combine them?
How?
Actually,
How would you deal with the left side? If your goal is to find the y prime.
couldn't you factor it out?
I can factor it out, it's a common term. Factor out the y prime, what would I have left? 5x squared plus 2x plus 2x4y. That's what the left side would be. My goal is to solve for the y prime, so now I can just divide both sides by this guy. So that would be 12x squared minus 10x plus 2 times y minus 4x cubed y squared all over 5x squared plus 2x plus 2x to the fourth one. And that is my derivative. Now don't be alarmed that there are y's in your answer. It would be equivalent if you were to replace each y by that huge expression that we had before. You'd realize that they simplified to the same answer. It will work. How could it not work? We're applying the laws of calculus. They work. So that's the derivative. Now that was a little hairy, but I guarantee you it's a lot less hairy than the quotient rule would have been on the first guy. Don't believe me? Go home and do it with the quotient rule on the expression that I did before. So there's sometimes when you have both options. Like I could solve this using implicit differentiation or explicit differentiation. Either way is not so bad. I could take it or leave it. Then you can have this kind of situation. I could do it explicitly, but why would I want to? But wait, there's more. What about this example? sure I'm writing down the right one. 2y equals. I'll save you some time here. It's impossible to solve for y. Like literally, I don't mean it would take a long time. I mean it's impossible to solve for y. There's no way to find a formula for y in terms of x in that equation. In fact, a long time ago, this kid named Galois proved that polynomials higher than the 5th degree do not have a general formula. You see like how you have a quadratic formula for second degree polynomials? Once you pass the 5th degree, no such formula exists. You can get lucky and find a formula, but it's not guaranteed that a formula exists. In this particular case, if I think of y, the polynomial in terms of y, this is a 7th degree polynomial. There is no formula to calculate y, and it turns out here you actually can't. Like you literally can't. There is no such answer. I would not be able to solve for y and say y equals this. Yeah.
Don't you do something with like Pascal's triangle though? Or like no? Or like polynomials?
That's to expand polynomials, that's not to solve.
Okay, something.
Like to write down y as a function of x, impossible. This has no solution for y. There's no algebraic formula you can write down to work this. So in this case, solving it explicitly is not an option. If I am studying two quantities and that's the relationship that they give me, and I want to talk about calculus, the explicit way of doing it is not an option anymore. Now I don't have a choice. Now I have to do implicit. But it's actually not so bad. Let's do implicit to find y prime. Well, how do we find y prime? Differentiate both sides, so differentiate one at a time.
2s plus 7y is 6 times y prime
Times y prime. You have to remember the times y prime because the y is a function.
minus 2y prime
Right? Equals
0.
0. Derivative constant is 0. So I just differentiated both sides and I got that expression. Y prime is the guy I care about. It's in two locations. How do I isolate it?
No, the factor it out.
Sure, on the left side I can factor, it's not here. But I could factor it out from
Yeah.
this guy
Yeah.
and at the same time move that guy to the other side. And so I can end up with my y prime is equal to minus 2x divided by 7y to the 6 minus 2. That is my derivative. Now, the derivative has y's in it, but that's literally the best I can get. It's impossible to actually write this as a function of x only. You might also notice here that we're dividing by this expression, so the derivative is undefined whenever the denominator is 0. In fact, this is the picture of that curve. Like that's not something we'll learn how to graph, but if you like plug it into a computer system or something and graph that, the graph would look like this, or something similar. You'll notice that there are a bunch of points where you have vertical tangent lines. At all those points, your derivative will not exist, right? So those will be the zeros of this guy. Right, it'll happen at 4 places. So a question you might have, no, we don't have any questions. A question you might have is, if I can't find what y is in general, how is this a useful formula to me? Y is in the answer, but we don't know what y is. Turns out it's still useful. I'll show you how. Here's an example. Find the equation of the tangent line to this guy at the point 2 comma 1. You guys remember finding equations of tangent lines? What do we need to find the equation of a tangent line? We need a slope and a point. A tangent line is just a straight line, so we need all the information we need for a straight line. How do we find the slope of a tangent line? Yeah? Derivative. The derivative gives a slope for the tangent line. We actually did that here. So given this question, the first thing I would do is I would find the derivative. My y prime would be minus 2x divided by 7y to the 6 minus 2. This was previously done. Which would mean I actually know the m for my tangent line here. What would it be? How do I figure out the slope at that point? Yeah?
Just plug in x and y.
Plug in that point into the derivative. That's how you find the slope at a specific point. The derivative gives you a formula for the slope of the tangent line. If you want to find the slope at a specific point, plug in the numbers for that point. In this case though, before we only had to plug in x values. Now we're plugging in both the x and the y values. So I can plug in the x value here, which is 2, over, I'm going to plug in the y value, which is 1. So my slope now becomes minus 4 over 5. So what's the equation of my tangent line?
Y minus 1.
Y minus,
Y minus 1.
so this means I'm going to use y minus y1 equals mx minus x1. So this becomes y minus 1, because that's the y value, equals m, which I just found is minus 4 over 5, x minus 2. That's the equation of my tangent. So even though my derivative has y's in it, it's still useful. You might still be bothered by this a little bit. Like, how would you know that 2, 1 is on the curve? Well, notice that if you plug in x equals 2 here, you get 4. Move the 4 to the other side, you get minus 1. So you have y to the 7th minus 2y equals minus 1. It's clear that if you plug in 1, you get 1 minus 2 equals minus 1. That's one option. There are several options, but you're given this point. But you see, that kind of thing of like plugging in one of the points and solving for the other one, that's the kind of thing that computers are great at. That we can do. I can't give you a formula for the function in general, but I can tell you about specific points on this function. Or at least I can approximate them to any degree of accuracy you need. You just run a computer program and a computer knows how to guess answers. We're not going to do it in this class, but there's a method that uses calculus to guess the answers. It's called the Newton-Raphson method. So your computer can have a program like that that it can't figure out the function itself, but it can figure out points along the function. Okay? So finding a point on a function is not super difficult in general for the typical things you would need. But finding a formula in general can be very difficult, even impossible, as it is in this case. And so we can find the tangent line. What we just did was we found the tangent line at the point 2, 1. So that's something like here, has negative slope. And so what's the use of knowing that? What's the point of knowing a tangent line? Yeah?
Instantaneous rate of change.
It's the instantaneous rate of change. It also is an approximation for the function, right? Remember, the tangent line is a line such that if you zoom in far enough, the curve and the line are doing pretty much the same thing. So if this curve is not easy to use, it's not easy to deal with because I don't know anything about it, it's much easier to use this because this is a straight line. I know everything about a straight line. And so, even though this is difficult to deal with in total, there might be a case where we know, oh, we're only interested in this point in time. What's going on at this point? And so I can pick a point, I can draw a tangent line, and then me studying this line is the same as me studying this function. Because if you think about it, we can't really get the exact answers in reality anyway. right? Everything we do as human beings is an approximation, right? You cannot cut a length of wood exactly pi units long. Think about that. How do you know if it's pi units long? You can only cut a wood within a certain degree of accuracy, as accurate as the machine you're using it to cut it with can cut it, right? So if your machine can cut within a ½ an inch accuracy, you'll just cut it within pi within a ½ an inch. You'll never get to actual pi. There's an infinite number of decimals. You don't know what the length is. You'll never be able to put that answer, like write it down on a piece of paper. You'll never be able to program in your computer. Do it this length. You plug in pi into a computer, it approximates it. It just goes to like 15 decimal places and it stops, and it uses that number. It's impossible to actually cut something. It's impossible to have a string of length pi, actually. It's not something we can accomplish. So approximations is where it's at, and that's why tangent lines are important. We can have very complicated things, but we use tangent lines to study them. And tangent lines won't give you the exact answer, but they're an approximation to the answer, and that's literally good enough, because literally everything we do is an approximation anyway. So that's one of the powers of calculus. You can study difficult things by studying a lot simpler things that are approximations to difficult things, but you can approximate to within any degree of accuracy you want. So if your machine can only work up to 15 decimal places, you can get an answer that's correct to 15 decimal places. You might not get the whole answer, but choose a number of decimal places, you'll be able to figure that out using calculus. So this is why implicit differentiation is important, even in cases where we cannot actually solve for the answer. Let's do another example. There's just a lot of concepts happening there. Let's just get back to basics. Let's just go back to computations. Give you a couple examples. I want you to find the derivative. Find y prime. 4x squared plus 2xy minus 3x squared y squared plus 4 equals 7 minus ln x. I think this was the bonus on the last quiz. To find the derivative, find y prime given that expression. Let's not worry about what that means or how it's useful, just find the derivative. By y prime, I mean dy dx in case it's not clear. X is my independent variable. There are times when x itself is another function. That's why I wanted to say that. Okay, go. What do we do?
8x.
Differentiate one at a time because there's the sum rule for derivative. Derivative of sum is the sum of derivatives. Okay, so this is just 8x.
Product rule.
Here you would need the product rule. That's still a thing. This is one function times another function.
2y plus 2x y prime.
Just perform the product rule on that function. Minus, what about this guy?
Product rule again.
Product rule again, because this is one function times another function. So what is that?
6xy squared plus 3x squared.
Well, minus technically because there's a negative here.
Yeah. 3x squared. 2y prime. Y prime again.
Okay. Just did the product rule here using the chain rule when differentiating the y function. Derivative of 4.
0.
Derivative of 7.
0.
Derivative of this.
Negative 1 over x.
So I've taken derivatives. Now I want to find y prime. What's the next step?
Subtract the terms that don't have one.
Subtract terms that don't have y prime. So there's going to be an equal sign. I already have that minus 1 over x over here. I can subtract 8x. Subtract 2y. Subtract 6xy squared.
Nothing plus.
Plus and that's it, right? So on this side, what would I have? Y prime is a common term.
2x
So I have 2x minus,
3x squared.
well, just write this as 6x squared y.
6x squared y.
And so then to find my y prime, I'll just divide. So it's minus 1 over x minus 8x minus 2y plus 6xy squared over 2x minus 6x squared y. That would be my derivative. It's a complex fraction, but we can multiply by x over x to kind of clean that up. I'm not worried about that at this point. Here's another example. Find y prime. E to the x plus y squared. What's the chuckle for? Ln of x plus y equals, find y prime. Yeah?
Would that be considered ln of u?
What about this one?
No, like for ln x plus y, is that the same as ln u? Like, do we use that rule?
Yes. So this is what I mean by if you're confused as to how to proceed, it's because you don't know the rules well enough. Being able to regurgitate a rule is one level, and that's the minimum you should be able to do. But you need to understand that rule in terms of a template, right? Here, if I'm differentiating this, what am I thinking about? It's e to a power. I just think of that as something like a u, right? So if I want to differentiate that, I'm going to use the rule derivative of e to the u, which we know is what?
E to the u times y.
Right, u prime e to the u, which means to differentiate this, I would take the derivative of the power times the original function. That's the rule. You have to see this rule fit on top of that in a template. In the same way, when you see something like this, ln of something, it doesn't matter what the something is. If I want to differentiate it, I just take the derivative of the thing over the thing itself. That's the rule. So I can fit ln of u on top of this. This guy would be like the u in the rule. Right? It's a template. It guides you as to what to do. Right? So I know that this guy is going to just be the derivative of the top over the derivative of this guy over that side. That will be 0. Now, let's go back to implicit differentiation, which is what's going to happen here. How do I actually differentiate x plus y squared?
Is it 1?
1, that's derivative of x.
2y, y prime.
Right. What's the derivative of x plus y?
1 plus y prime.
So that's the first equation. But the goal is to find y prime. How do I find y prime? Oh, algebra. Algebra is how I find y prime. Easier said than done, right? Here your y prime is kind of stuck in parentheses. The first thing to do if something is stuck in parentheses is to get it out of the parentheses if you want to solve for it. So what I would do is distribute. This is e to the x plus y squared plus 2y prime times e to the x plus y squared plus, here I have a fraction, but we can split fractions across the numerator, so I can split that up into this stuff. Now I have my y prime terms isolated. How do I solve for them? Algebra is how to solve for them. So when I isolate terms, you do it the same way. Move everything that doesn't have the term you want to the other side. Factor out the term you want, divide by the thing. Which means here, if I leave these on that side, my y prime is a common term, so I would have y prime times 2y e to the x plus y squared. That's this. Plus what?
plus y.
1 over x plus y, and that's it, right? That takes care of this guy. The others don't have y prime in, so it's equal. What do we do?
Move them on.
Move them to the other side. So I subtract this. It's this. And I subtract that. It's this. We've accounted for everyone. Now I'm just going to divide both sides by this guy. So that means my y prime over 2y e to the x plus y squared plus 1 over x plus y. At the moment I'd accept that answer, but it is a complex fraction. You can simplify this. You could multiply, for example, by x plus y over x plus y, and you would get y prime is equal to that's still a fraction, but it's a simpler fraction. So this is finding y prime using implicit differentiation. As you can tell, you need to know the rules like the back of your hand to be able to apply them here. It's why on every quiz I grill you on the rules. It's important. Okay, so here's an example to try on your own. The homework for this won't be due on Tuesday, but you can work at it. So this is an actual example, meaning it's not just a makey up question like I did here. This is called van der Waals equation for a specific gas. For those of you who, I don't know if you're doing chemistry, what point in chemistry you're at, but this is a thing. It's like a thing. Van der Waals equation.
You were in this today.
Huh?
You were in this today.
You did this today?
Yeah.
Awesome. So do you guys know what that equation is? That's a total coincidence. I did not plan that. This was written a long time ago.
You're too excited about
Like, coincidence like that don't happen all the time. It's just-
dust field, dead
Oh
mathematics.
Steve.
Okay,
I was just
so
thinking about this.
you guys can explain to me where this came from, because I don't really know. I just know it's a thing.
It's not nice.
Yeah. Okay.
I don't
So-
like it.
So if you think like this is never a situation you'd have to encounter, you encounter things like this where relationships come to you and it's messy. You don't. This is P is pressure, V is volume. You don't just have P as a function of volume and it's all nice, right? Or you don't have volume as a function of pressure and it's all nice. The things are mixed together. But I still would be able to want to answer questions like, how is the volume going to change if I change the pressure in this way? Or how is the pressure going to change if I change the volume in this way, right? I don't like this formula for van der Waals equation. Can I use a straight line to approximate it at some point of interest, right? These are still questions I'd want to be able to answer. And so you can use this and find something like dV/dP. So that's the guy that will help you to know how fast will your volume change if you're changing your pressure at a certain rate. So let's say you're increasing the pressure by 1 atmosphere every minute. How will that affect your volume? You can use implicit differentiation to figure that out. Total coincidence. Okay. So that's an example of why we would need implicit differentiation, because these things actually do occur. Like someone sat in a lab and figured this out, and that's how it came out. That was just the result. Let me mention a little bit about log differentiation. We'll do more on this next time. I'll just give you the method and I'll talk about one instance in which we want to use it, but then we'll cover other instances next week. So here it is as a method. Let's say you're given something and it's in the explicit case, and you want to find, it can probably work in some implicit cases as well, but let's keep it simple. We want to find y prime. Here's a method that could possibly work. You don't apply it literally every time. Sometimes if this is easy like x squared, you won't do this. But the method says the first thing you're going to do is take the log of both sides. You can look back at my proof for the power rule. I actually used log differentiation. I just never said I was using it at the time. The second step would be to differentiate both sides. Now it turns out the differentiation here would be implicit. So you differentiate both sides implicitly with respect to x. 3. A y prime is going to pop up. Solve for y prime. Because that would be the point of interest. Now, let's use it to derive a formula that you guys used in 3.4, which, by the way, we have homework due today, but I'll leave 3.4, don't hand it in, because I want to do this. So, if my y is a to the x, find y prime. Given that, what would you think? What would derivative a to the x be? Huh? What rule would you try to apply?
It's thinking power.
Could you use like
You're thinking power rule, but that was the wrong thing to think.
Yeah.
Why is it the wrong thing to think?
It's an exponential.
Okay, so remember how I said you need to remember your formulas specifically in terms of being able to use them as templates. Now in the power rule, and this is also why I said you need to memorize both sides of each rule so you don't get mixed up by things. The power rule says this, right? E equals nx to the n minus 1. So I'll have a lot of students who see this and they think the answer is xa to the x minus 1. That would be wrong. Why is it wrong? Because in the power rule, what is the base? The base is the variable, right? And the power is the constant, right? In this situation, it's completely opposite. The base is the constant and the power is the variable. Which means using this as a template cannot work. It doesn't fit on top of it. They're not the same thing. You cannot use the power rule on something like this. Just because it's raised to a power doesn't mean, oh, power rule. That's not, no. Power rule is a very specific rule that applies to a very specific kind of function. That's not the kind of function you can apply this rule to. So the power rule would not be, you might think it for a second, but then you're supposed to slap yourself across the face for being so silly. And then go through some sort of penance, right? Because the power rule does not apply in this situation. But so having a variable in the power is kind of complicated, but logs get rid of powers. This is one of the reasons why we use a log. So I would think of something like log differentiation in this case. So I would have set y equals a to the x. What I would do is take the ln of both sides. What that allows me to do is get out of a situation where I have a power in the first place. Now, what I can do is I can differentiate this. What's the derivative of ln of y?
1 over y prime.
Implicit differentiation takes effect, the chain rule here, so it's y prime over y equals this side. You're thinking too complicated. ln of a is a constant, because a is a constant. You have a constant times x. What derivative of constant times x? 1 times the constant, so it's just a constant.
Yeah.
Our derivative of constant times x is just a constant. So that's the derivative of that side. And so now what I do is the next step, solve for y prime. So the idea is you take log of both sides to simplify it. because there's some kind of issue that a log is useful in simplifying. So like, if it has a power that you don't know how to deal with the power, to bring that power down, you can use a log. So here I'd solve for y prime, this would actually be y ln a. What is the y?
It's a to the
It's
x.
a.
So it's a to the x. So this means that y prime here is a to the x ln a. This gives you another rule that you have to memorize now, so this is just something that we know now. And with this you can complete the homework 3.4. The derivative of a to the x is a to the x ln a. There is a chain rule version. The derivative of a to the u is equal to u prime a to the u ln a. That's the main start of section 3.4, so you can do homework for 3.4 now. Homework for 3.1 and 3.3 I will take off you now. But we'll stop there for now. I'll give you a lot more scenarios in which you might want to use log differentiation and how you can know if that might be something you want to do.
So
Yeah.
homework 3.4
Homework 3.4 is due on Tuesday. Homework 3.1, 3.3 is due now.
Yes.
Homework 3.5, I didn't finish that section, so no, that's not.